Everybody, and welcome to part 3 of our 4-part video series on building large language model applications. In this video, we're going to dive into RAG, or Retrieval Augmented Generation. This is a method that really allows us to uh, inject new knowledge into the model without having to do training, right? So if you're not familiar with training large language models, it's very expensive. And while it certainly has its use cases, and we may even make content on that in the future, it's a little outside the scope of this. And it's also usually not the best first step when it comes to trying to teach the model new information, especially if you have a good set of documents to start with. So in order to run, we are going to install some packages. Again, if you've been following up to this point, you probably have most of these installed. But the new ones we're going to be installing are Quadrant Client and Llama Index. So Llama Index we're going to use for essentially the loading step of our RAG pipeline, and we'll take a look at that soon. And then Quadrant Client for our in-memory vector store. So again, make sure you have those installed. And once again, if you don't have the model running with VLM, you can copy this command here and again, just pop that into the terminal, right click and paste, and that'll take a minute to spin up. So to get a good sense of where RAG becomes useful, let's generate some documents, and I'll explain why we're doing this in a minute. So let's pretend that we are an airplane manufacturing company, right? So we create airplanes, and we're going to ask the model to create us 3 fictitious airplanes, right? About their gas mileage and their specs, their controls, their size, all of that. So we're going to define a system message and user message. Again, we're going to connect to our model. And then we'll give them some names. I came up with these 3. You can use the same ones if you'd like. And then again, just like we've been doing before, we're going to create some responses. Now, if you are using the same names here in the same model, you can set this seed here. I set it to 117, and this is basically a way to replicate the results. But again, feel free to change this around. You can use different documents. You may just have to ask a slightly different question, but should get the same gist. Now, before I ran this, I also came over here. You can right click, create a new folder, and I named it docs, and that's where all of my documents are getting filled out. So if we take a look at like Blue Falcon, this was generated by the model, and it's just thrown into a text file, so we get some specs, some information about maintenance and controls. So it's completely fictitious, right? So let's say that we wanted a bot that could answer questions about our airplanes, right? And the idea is that this is meant to represent internal or proprietary data. So if we think about the way that models are trained, right? They're trained on data that's out on the internet, right? So typically they'll go out and they'll web scrape to grab all this data and they train on that. But that requires the information to be publicly available, right? So if you have these proprietary documents that are only internal, right? Maybe they're on your SharePoint and nowhere else. The model's not going to know about it, especially if there's no reference to it on the internet. Now, we kind of faked this by coming up with fake airplanes, but you can imagine if you had a product that was called Blue Falcon 993, right? And it's not anywhere on the internet, the model's not going to know about it. And we can actually confirm this. So let's say, hey, model, tell me about Green Sparrow's fuel efficiency. Again, we're going to use a really simple system message and user message here. Just, hey, you're a helpful mechanical assistant. Give me a nice answer. And when we run it, we see that it's like, hey, there's some confusion. It's a bird species, not a vehicle or a machine. So it's very confused. It doesn't know what we're talking about, and it makes sense, right? Because this is fictitious data. It's proprietary. It's something that the model has not seen. And this is where RAG shines. We can supply the model with documentation to create our own internal knowledge base so that the model can refer to it to help answer questions. And we can do all this very quickly without needing to spend a ton of time and resources doing a really big training. And again, training has its place, but RAG is always like a pretty good place to start if you have a similar use case to this. So let's take a look at the ingest process here, right? So there's really 2 sides to RAG, right? Um, there's the ingest process and the query process. So if we take a look at this, we break up the ingest process into 4 steps: loading, splitting, embedding, and storing. So we first load our data. These could be Word documents, PDFs, text files. We're only using text files for now, but you can easily modify this for other text formats. Data is then split into smaller chunks, and there's various methods for this. We're going to go with a pretty just bare bones like chunk by token length, but there's semantic similarity. There's splitting on sentences, splitting on paragraphs. I mean, there's whole different types of splitting methods, and this is actually a really big place for improvement. So if you have a lot of documents with similar formats, you could even make your own splitter. So we took our document, we split it up into chunks, and then we passed these chunks through an embedding model. We'll get to embeddings here in a second. Um, and then the last step is we store these embeddings in a vector store. So in the next section, we'll take a look at embeddings. All right, so what are embeddings, right? You had me up until we got to embeddings, and now I don't know what's going on. That's weird. What are you talking about? Embeddings, for all intents and purposes, right? When I'm saying embedding, I'm talking about a vector, an embedding vector, or really just a list of numbers. So a vector could be something like this, right? We see it's basically a list of numbers, 1, 2.8, 4.1. That's a vector. Now, embedding models specifically are AI models that take in a variable length piece of text, but they generate a fixed length vector. So I could take in a sentence, I could take in a paragraph, I could take in a whole book, but if the length of the model's output is 384, right? 384, or let's say 3, right? In this case, let's say the model always generates 3. No matter how big the input is, I'm always going to get a size 3 vector, right? Or if it was 384, it's going to be 384 or 786, but it's always the same length, right? So in this case, let's pretend that I have an embedding model. It has an embedding dimension of 3. The dimension means how big those lists of numbers, those vectors are. Right? I can see if I passed in the words baseball, basketball, and Linux, I might get something like this. 1, 2.8, 4.1 for baseball, 1.5, 3.2, 3.7 for basketball, and negative 2, 2, and 1 for Linux. Now, if we plot these three vectors, we'll see that if we plot these together, we'll see that the first two, baseball and basketball, are pretty close together, but the last one, Linux, is pretty far away, right? And this is because semantically, if we think about intuitively, again we came up with these numbers, but intuitively, the reason that it looks this way with embedding models is that they are semantically similar. They're both sports, but Linux is an operating system kernel, right? It's all the way over here. It's a completely different domain. Now, if you want to copy this code, feel free. We took Plotly and NumPy. We just defined these NumPy arrays, built them out as vectors. We did some basic formatting. I won't get too much into this because this is really Plotly stuff, just to demonstrate, but feel free to pause and copy this out if you want a visual reminder. Um, However, typically embedding models are much bigger than an embedding dimension of 3, right? A lot of times they might be 384, 768, 1024. I personally cannot visualize that many dimensions, so I like to start with 2 or 3. But you can picture, right, instead of having these lists of 3, we have lists of maybe 768. So let's say we had a embedding model with a dimension of 768. You can see if we put in Red Hat Enterprise Linux and DNS stands for Domain Name System, both of them produce a list of 768. Right, so again, just reiterating, no matter how long the text is, we get these vectors. And the idea is that these vectors represent the semantic meaning of the text, right? So going back to this picture, things that are similar are closer together in that vector space, but things that are dissimilar are farther apart. This is intuitively the magic behind RAG, right? Because now what we can do, right? And actually, I'm getting ahead of myself a little bit. Let's pull this down and really see this in action. Um, so if we load in VLLM, we can load an embedding model. I'm using int float e5 small v2 off of Hugging Face. And we can see that if we pass in some text, we can grab the embeddings from it. We see that I grabbed the first 3, but the actual length is 384. So again, all of the vectors that it generates are going to be 384 numbers in length. And if I pass in to this actual embedding model, what is Firefox? Which is a question. And then let's say I had a document chunk. Firefox web browser is maintained by Mozilla. And then as a Red Sox fan, I had to throw this in. The Red Sox beat the Orioles 8-4 in their game on April 3rd, 2025. Um, right? So intuitively, before we even get into the embeddings, you would think if I asked this question, I would want this first document to be part of the context that the model can look at to answer the question. Probably don't care about the Red Sox game for this question, but maybe if I was asking about, the Red Sox and Orioles schedule or baseball scores, I might want that. So we can pass all these in. So we'll do embedding model dot embed for each of them. And we'll grab their embeddings. And then using sklearn's cosine similarity, we can measure essentially how similar these are. So you can think of this as sort of a score of how close together they are. So closer to 1 means they're very similar. Closer to 0 is farther apart. And so if we compare these, we see that Q1 and document 1 are a 0.87, so very high. Q1 and document 2 are a lot farther apart. It's over 10. It's a 0.16 apart, and then the two documents are even more dissimilar than that. So what does this mean for us, right? Let's pause. What does this mean for us? Well, intuitively, if we had a collection of documents and we had a question come in, right? So we have our collection of documents and our question. We could embed the question, search through and compare to all of our documents embeddings, and then pull back the ones that are the highest score, that are the closest together, right? Meaning that instead of having to bring in all the documentation to the prompt and give all of that information to the model, we can search for the most similar stuff by our embedding metric, right? So the stuff that scores highest on this cosine similarity score, we can bring that into the prompt and give the model relevant information. So that right there, what we just went over, is the magic behind RAG. Now, there's a ton of innovations that have been done. There's hybrid RAG. There's even things that are looking at like graphs with graph RAG. But this is the foundation of RAG as we know it. So with that, let's get into the actual process of loading some data, splitting it, and going through our ingest process. All right, so we've gone over embedding models. We feel pretty confident about everything. Let's get into actually creating a simple RAG pipeline. Now, again, this is all for show. This is not, for learning. This isn't a production setup, but it'll get the point across and give you enough to get going. So again, this is where we're using Llama Index. So they have this really neat tool called Simple Directory Reader. And what we can do is, again, we have this directory of documents. We can actually point at it and load all of them in, and we end up with a list of 3 documents. And if we look at the text from the first document, we can see it's the text out of that file for our fictitious airplane. So that's our load step, right? Very simple. Of course, if we had PDFs or Word documents, that might look a little different, but because we have some basic text files, it's pretty straightforward. And then we're going to use Llama Index's ingestion pipeline and sentence splitter. Now, again, I know I said that we weren't going to touch libraries a whole lot, but I figured to keep this as simple and straightforward as possible, we're going to stick with Llama Index for this basically splitting. But you can do all of this manually. It would not be hard, but just to keep the code shorter because they have a really, really simple abstraction here, we're going to use that just to split the data up. But we'll do the actual search and RAG, all of those bits by ourselves. So we can define a chunk size, right? So we're just going to split by tokens. So we're going to define a chunk size of 200 tokens and an overlap of 25. So what this means is we're going to split our documents up into 200 token chunks, and then they'll overlap 25 tokens. And this kind of helps just make sure that each chunk kind of has context of where it's coming from. And then we're going to define an ingestion pipeline. So this is one of my favorite bits of Llama Index. You can create an ingest pipeline, and then you supply these transformations that it's going to run. In this case, it's going to be a sentence splitter with these chunk parameters. And what we'll get out is basically a collection of nodes, or really just chunks that are now this smaller size. So we went from 3 documents to 10 chunks. You can imagine if you had much bigger documents and a lot more of them, you'd end up with a lot more chunks. And then we'll loop over those, and for each of them, we're just going to pass them through our embedding model and get their embeddings. So now we've loaded our data, we've chunked it up into smaller chunks, and we've created our embeddings. So now we need somewhere to store this, and this is where a vector database comes into play. Now, for simplicity's sake, because we don't really want to deploy. We're not looking to deploy Postgres and PG Vector or some big cloud thing into this. We're just gonna keep it simple with Quadrant Client, which we can just run in memory. So we'll deploy Quadrant Client, and what we're gonna do is define our embedding size. So for this model, it's 384. And again, where I got that from is um, if we go back to our model and we looked at one of our embeddings, we can see that it was length 384, right? So that's our embedding dimension. So we'll create a collection, and this is just going to be basically a grouping to store our documents, and then we're just giving it our embedding size and saying, hey, we want to measure the distance by cosine distance. There's different algorithms you can use. Cosine distance is a pretty common one, but you can feel free to play around with different algorithms. They all have their own pros and cons. And then basically for each node, we're going to iterate over them and place them into our collection. Each point in the collection, so it's basically a collection of points. Each of the points is going to have an ID, which is just going to be basically the place in the list. It's going to have its vector, which is the embedding, and then we're going to give it um, basically just this colored payload for uh, if we wanted to like do some visual stuff. And that does it for our ingest. So now we'll step into taking a look at how we can actually use this ingested pipeline and the data we just created to search for information. All right, so we've taken in our documents, we've chunked them up, we've gotten our embeddings, we're ready to go. So let's take that same question from earlier. Tell me about the green sparrow's fuel efficiency. We're going to start by embedding it, and then we'll have our embedding vector, again, 384. And what we'll do is we're going to do our client. We're going to query for the top 5 points based on this query embedding. So what is this doing? Well, it's going to use that cosine distance algorithm to find 5 points that are most similar to our question, hopefully pulling out the most relevant information. And if we loop over these points and look at their scores in the text, we can see that the top one is Green Sparrow, some text from Green Sparrow. We get some from some of the other documents, right? Because they are all pretty similar. But we can see that the top one is our Green Sparrow document. And then what we do here is essentially we're going to take our same prompt from earlier, but now we're just going to have this new context section. So what we'll do is we'll loop over all of the text that we retrieved. And we're going to just join them together. So you can imagine that we've just taken the top 5 most relevant texts that we pulled back, and we're putting them in the prompt. And again, you could change this. You could do the top 3 if you wanted, right? You could do the top 2. But for now, we're just going to stick with the top 5. And what we get back here, we can see that it's actually answering based on the document. It has a maximum range of 5,000 nautical miles. And we could actually go take a look at this and verify that, right? So yeah, maximum range of 5,000 nautical miles. So it's actually telling us about the airplane that we uploaded, right? So that's RAG, right? We took some documents we had. We realized that our model didn't understand the information in them. We chunked them up, we embedded them, we stored them in a vector store, and then we queried against it. And we were able to pull back data without having to do any training. Now, again, of course, there's a ton of improvements you can make to this by using a more production grade deployment for a database, by tweaking the embedding model, using a bigger LLM, using different chunking strategies. And I highly recommend playing around and seeing like how those different parameters and components can affect the performance. But that does it for our RAG video. Thank you for sticking around, and I'll see you in the next video for our agents. So have a good one. Goodbye.